Hi, my name is Aoi Yamato. I'm a master student at Keio University, and today I would like to present a pre-training framework for molecular property prediction capable of handling complex compounds. Drug development is very expensive and time-consuming, usually taking 10 to 15 years and costing billions of dollars. Also, the number of possible compounds that can be created even for small molecules, is extremely large, about 10 to the power of 60. To deal with these challenges, drug discovery has started to use more data-driven methods in recent years. Machine learning models for predicting molecular properties are now important tools for finding molecules with the right characteristics. These models use inputs like smiles, molecular graphs, and fingerprints to create useful representations for predictions. In past research, different pre-training methods have been suggested to handle the problem of limited labeled data. It is important to note that many of these models restrict the training data to drug-like molecules and do not handle large and complex molecules like natural products. However, as shown in this figure, about 50% to 60% of approved drugs are based on or inspired by natural products. Also, large-scale databases of natural compounds have been made publicly available, allowing for their utilization in deep learning models. Despite playing a significant role in the drug discovery and development, it is often not used in molecular property prediction learning. In this work, we aim to develop a molecular property prediction model for complex compounds by introducing molecular fragmentation, a large-scale pre-training strategy, and incorporating additional knowledge. Now, I will explain the methods. The model we developed, Fragment Tree BERT, FT-BERT, consists of two main stages: pre-training on unlabeled compounds and fine-tuning for downstream tasks. We use approximately 2 million molecules from the Kembo dataset to pre-train FT-BERT. For the fine-tuning phase, we use Moleculase, which provides 30 bioactivity datasets, and the TDC ADMET benchmark, which focuses on toxicity profiles to predict molecular properties. This architecture has three key components: molecular fragmentation, tree positional encoding, and molecular descriptors add additional knowledge. First, compounds are decomposed using Briggs rules and ring structure extraction. The resulting fragment trees are then input into the model. Second, we calculate the positional representation for each node. Finally, we compute the interrelationships between all nodes using these fragments and molecular descriptors. Next, I will present the results. The table shows the averaged RMSE results for FT-BERT and the baseline of 30 bioactivity datasets from Moleculase, evaluated on both the plotted set and specifically on activity cliffs. The results indicate that our model achieves lower RMSE on half of the tasks, but struggled with activity cliff predictions. The figure below compares FT-BERT, the baseline, and fully connected model using ECFP on classification and regression datasets from the TDC ADMET benchmarks. As shown, our model outperformed the ECFP model, but was outperformed by KPZT. We believe that with the use of molecular descriptors, the molecular representations generated by our model include not only structural knowledge, but also the semantic knowledge of molecules. While our model was able to capture the microscopic structure of molecules, it struggled to learn the local structures that influence activity cliffs. To verify whether this model truly fails to capture activity cliffs, we visualized the embedding vectors of the molecular representations using UMAP. Here are the results. Although FT-BERT could not accurately predict values of activity cliffs, we visualized the molecular representations of pairs of activity cliffs that correctly predicted using FT-BERT. As seen in the figure, while ECFP and molecular descriptors are positioned very close in Latin space, FT-BERT's embeddings are located at distant positions. That's all I have to say about the experimental result. In summary, FT-BERT can generate molecular representations that incorporate both structural and semantic information, and it performs well with larger molecules, but struggles to capture fine structural details, such as those found in activity cliffs. In our future works, enhance fragmentation rules to capture local molecular structures better, and broaden the dataset by adding more compounds, including natural ones. Thank you for listening.